It is my pleasure to introduce my former PhD supervisor, Professor Rebecca Hodge, from the Department of Geography at Durham University. Her research focuses on fluvial geomorphology, particularly around sediment transport and flow processes within river systems. She's been using numerical modelling, field measurements to understand how sediment moves and interacts with river channels using techniques such as cellular automation models, CT scanning and terrestrial laser scanning. She completed her PhD at the University of Cambridge before working as a postdoc at Glasgow. She joined Durham in 2011 and became a professor in 2022, and her contributions to geomorphology have been recognised with the Gordon Warwick Medal from the British Society of Geomorphology. And she also did my PhD, as I said, about listening to rivers, which is a far bigger accolade than anything there. And today she'll be talking on how rough is a river, predicting how flow in upland river channels occurs. So please welcome Professor Rebecca Hodge. Yay! And I'll stop on Carol.
Excellent. Thanks, Alex, for the introduction. Also makes me realise I should update the text on my university webpage.
Exactly. That I know.
But yes, thanks for the invitation to talk today. So what I'm going to be talking about is our current project, which is on flow resistance in rough bed rivers. And to be honest, most of the work that I'm presenting today is actually all been done through to the hard work of the people pictured here on this slide. So Bobby Housego, who was a postdoc at Durham, is now at Loughborough, David Whitfield, who's taking a break from his PhD to do some work with us, Rob Ferguson, who many of you may know, and then there was Thais Yamasaki, who is also a postdoc at Durham at the moment. So like I say, they really take all the credit for all the work that I'm going to present today. So there we are. So I'm told that I understand that you're a bit of a mixed group of people. So I thought I'd start kind of with some of the basics. And so in this project, we've been really trying to think about flow resistance in river channels and how we can make better predictions of that. And just to, I guess, kind of say, what do we mean by flow resistance? Well, we're really thinking about the way that the shape of the river channel slows down the velocity of the water within that channel. So, for example, if we've got two river channels here, we've got one river channel that's got a very smooth boundary, so a smooth bed and smooth banks, and another example here that's got far rougher channel. So this one's got a load of big boulders and stones within it. If everything else is the same, so the width of the channel is the same, the slope of the channel is the same, and we put the same discharge of water down through those two river channels, then in this smoother channel here, because there's less friction between the water and the bed, there's less energy extracted from the flow, and therefore that water will have a higher velocity. So we're going to have a higher velocity in the smooth one compared to the rougher one. Because the water's got a higher velocity and because of the continuity of flow, we're actually going to have a shallower flow here. So where we've got a smoother channel, we're going to have faster flow. It's also going to be shallower. When we've got a rougher channel, we're going to have slower flow, and therefore it's also going to be deeper. Being able to understand that or make that prediction is important for things like looking at flooding. So clearly, if we've got slower flow, we need a smaller discharge before we're at risk of flooding. So it's important for understanding flooding at that particular location. It's also important for understanding flooding downstream, because if you've got faster flow, that water is going to move more quickly out of that section of channel and be conveyed more rapidly downstream. So it might not cause flooding at that location, but there might be increased downstream flood risks. If I asked you how to predict roughness of river channels or how to predict flow resistance, most of you, I imagine, would say Manning's N. And this is an approach which, you know, some of you might have done like GCSE geography or the standard grade geography, and you will have often gone and measured a river and calculated a Manning's N for that river. So Manning's N is really used in this very simple equation where we can predict the velocity of the river as a function of the hydraulic radius, which is basically the cross-sectional area divided by the wetted perimeter, multiplied by the slope, and then divided by this Manning's N value. So basically, if we've got a rougher river, we have a higher value of Manning's N, and therefore we have a lower velocity. In order to kind of calculate this value of Manning's N or to identify one, a lot of the times you would do it quite sort of empirically. So you would go to a table like this one developed by Chow in '59, and you would look at the descriptions and you would find a description that matched the river channel that you were interested in, and you'd select a value out of that table. You might also go to some other publications. So this is one produced by the USGS in '67, where they basically went to a whole load of rivers. They calculated the flow properties of those rivers, and they back calculated Manning's N. And it's essentially a booklet with lots of details about different rivers and photos in it. So you can kind of go through, find one that matches the particular location that you're interested in, and again, use that to identify a suitable Manning's N value for your particular river. However, this idea of kind of selecting Manning's N from an image, it's not a very precise way of doing it. And other people have tried to develop more sort of quantitative methods for looking at Manning's N. So one way of doing that is by using the riverbed grain size distribution. So for example, this is a slightly sediment covered riverbed, but if we think about coarser grain sizes are going to produce a rougher riverbed, which we would expect to have a higher flow resistance. So you can go and measure the grain size distribution and measure the median grain size, so which is known as D50. And then you could use equations like this one by Carson and Griffiths in '87, where basically you can calculate Manning's N as a function of that D50 grain size that you've calculated. So that all kind of sounds great. However, one of the problems with using Manning's N is that people have shown that as the amount of water in the river increases, the Manning's N value decreases. And this is because basically as you've got more water, the water doesn't feel the effect of the surrounding bed and banks quite as much. So Manning's N, if you measure Manning's N at a low flow condition, it might not be applicable to the high flow conditions that you're really interested in. So people have suggested that actually what we should be using is kind of more theoretically robust relationships, such as the Darcy-Weisbach friction factor, which is represented by an F. So the part of the reason that the Darcy-Weisbach friction factor is sort of more robust is that it predicts flow resistance, not just as a function of grain size, but also as a function of flow depth. So it's a function of basically the depth of the water relative to the grain size. So you're effectively looking at the relative submergence of those obstacles in the river. So it is a more robust way of predicting flow resistance. However, it's still got this grain size component to it. And that works fairly well in a number of rivers. But in this project, we're really interested in looking at kind of upland rivers. So uplands, sort of upper streams, the sort of small headwaters of a lot of river basins, which actually, because they're very small and abundant, they're actually a very large proportion of the total river network length. If we go and have a look at kind of what these upland rivers look like, these are some examples. And you can see that, they're really sort of quite complicated systems. They've typically got things like overlying sediment. They may well also have quite a lot of bedrock in them. So this is the River Garry here, and you can see these very steeply dipping bedrock ribs. We've also got a lot of boulders, and those boulders may well be quite an extreme end of the grain size distribution. They also can be characterized by rough banks as well, such as these ones in Trout Beck, and also these examples over here. The shape of the bedrock in these systems depends on the rock type. It also depends on the structure of the rock, so whether it's bedded, whether it's jointed, and also the way in which that rock is eroding. And I guess the kind of key point here really is that the grain size, and a percentile of the grain size distribution, so things like the median grain size, or maybe the D84, so the 84th percentile of the grain size distribution, that really doesn't describe the shape of these channels. That's not fully describing the topography that the flow is going to be experiencing as it goes down those channels. And therefore, it's not going to give us good predictions of flow resistance. To just kind of, I guess, extend this a little bit further, particularly a subsection of these channels that we're interested in are these types of bedrock channels. And this is just to give you an example of some of the variety that you might see in bedrock channels. So we've got limestone ones where we've kind of got these almost sort of solution structures. We've got things like here that the River Tees, which is an igneous one that I think Alex actually came and helped out. So with the field work on this day. And again, we've got a lot of plucking, so it's quite a blocky structure. we've kind of got these limestone ones which are continuous with the bedding. So this is the top of a bedding plane. So we've got a very smooth surface. And then things like abraded ones where we've got sediment which is going along and bashing against this surface and kind of smoothing it out. So again, we've got a lot of variety here. And as you can see in each of these cases, the shape of the size of the sediment is not the thing that's going to be determining the flow resistance. Just as an aside, this is a terrestrial laser scanner, which is a survey tool that I'll come back to later. So the aim of this project was really to try and develop new methods for predicting flow resistance in these kind of upland channels. So we've kind of named these rough bed rivers. So there's kind of two steps to what I want to present today. So the first question is, we've got these rough bed rivers. It's like, what metrics should we be using to describe the topography of these rivers? There's a whole range of different roughness metrics in the literature, which ones are most appropriate. And then the second question we want to look at is really this question about, how does the shape of these river channels, how does the roughness of the bed and the roughness of the walls affect the flow resistance? I should add that quite a lot of this work, particularly the flume work, is very much work in progress. So it may still be a little bit rough around the edges. Part of the reason for going to look at these questions now is really because of the availability of new survey methods. So things like terrestrial laser scanning and structure from motion photogrammetry have really opened up a whole range of possibilities in terms of the types of data sets that we can collect. So these are some example data sets. Again, this is those examples from the River Tees. And you can see that we can now collect sort of centimetre, if not sub-centimetre scale topographic data from these surfaces. So we can capture their topography at very high resolution. I guess there is a caveat here that these are all data from exposed surfaces, and it's far harder to do it from submerged ones. Another reason for kind of looking at this problem now is that actually this is not a problem which is unique to geomorphology. There's a whole range of disciplines who are interested in the way that flow over a surface is kind of disrupted by the shape of that surface. So, for example, there's a lot of engineering literature. So things like ship hulls. If you've got barnacles on a ship hull, that's going to affect the drag on the ship and hence the fuel efficiency. Things like flow over buildings, kind of looking at dispersal of pollutants in urban areas. Things like artificial flood relief channels and soil erosion. They're all examples where we've got flow moving over an irregular surface. And so it's actually worth looking at kind of those disciplines to say, okay, well, what sort of approaches do they use? A lot of those examples are not exactly the same as rivers, particularly because in rivers, we're dealing with quite shallow flows and we've got a free surface, which is often quite close to the rough boundary that we're looking at. Whereas in a lot of examples, the flows are far deeper. So they're not directly transferable, but it's still useful to kind of take examples from them. And then this is kind of what work that Rob Ferguson has been doing this last year. So Rob has actually written a review of looking at these other disciplines and kind of identifying what we can take from them and actually bring that to fluvial geomorphology. And what he found from doing that review is that there's a lot of good evidence that if we want to describe the shape of a surface and the way that that's going to slow down the flow, looking at the standard deviation of elevations is a very good starting point. So the standard deviation is basically telling you about the range of elevations over that surface. So is it a surface with a very big range of elevations, or is it quite a smooth surface? However, the other disciplines have identified that often one metric is not going to be sufficient. So two metrics that they've particularly identified as being useful. So one is frontal area. So frontal area is basically tells you about the blocking of the obstacles that are kind of blocking the flow. So for example, in these two examples here, we'd have the same standard deviation, but actually the frontal areas you can see are quite different. In the left one, the obstacles are flow aligned. In the right-hand one, they're going to be blocking the flow. So we actually might want to consider frontal area when we're trying to identify flow resistance. Another metric which has been identified is skew. So skew basically tells you about the shape of the distribution of elevations. So whether you've got a few number of very high ones or a small number of very low ones. So these surfaces, again, have got the same standard deviation, but different skews. And you can see that where we've got the obstacles which are sticking up, they're going to block the flow, and they're far more likely to have an impact on the flow compared to a flat surface where we've got the same size holes in the surface, where the flow can just go over the top of them. So skew is likely to be another important metric for understanding flow resistance. So what we did was we kind of said, okay, well, how can we describe channel topography? So we took our data set, which was 20 different reaches from 10 different rivers, and we took our high density point cloud data from all those different rivers. We gridded those all down to 5 centimeters because we wanted to have a uniform spacing in each of those different examples. We've got data from sites with a range of channel geometries, so widths and depths, a range of different bedrock exposures, so some are fully alluvial, some are fully bedrock, a range of grain sizes, including sites with boulders, and a range of different channel gradients. And then what we did was we then took a whole range of different roughness metrics, and we calculated the metrics for all those different channels. So this table, this shows you the properties that we calculated. We identified a kind of different types of metrics of looking at the roughness. So some of these metrics are based on the entire surface elevation. So we're basically taking all the points across the surface, and then we're just calculating averages from all those, or calculating summary metrics from all those points. So things like the standard deviation, things like the range and the skewness. Some of the other metrics are kind of a bit more based on looking at where points are within that surface. So things like slope, curvature, rugosity are basically taking into account the elevation of one point next to the following point. So you're doing things like calculating the slope of the surface and calculating the total surface area, 3D area of that surface. We've also got metrics which are kind of direction dependent. So things like the frontal area, where we're applying a downstream flow direction and working out the kind of blocking area of that surface to that flow direction. And the inclination index is another example of a kind of directional metric. And another one that an effective slope is another one, again, that's quite widely used in the engineering literature. Another thing that we also looked at is with the metrics is that you can calculate metrics at different scales. So you can either calculate them using the entire data set, or you can kind of break the data set into smaller windows and calculate those metrics over those smaller windows. So we also calculated some metrics where we changed the size of the window over which we are calculating those metrics, and basically looked at how the value of the metric changed as a function of that window size. So we then had a very large amount of data from these different rivers. And some of that is summarized here. So each of these plots basically shows a different metric, and then each of these points is the value of that metric for the individual rivers. And I think really I'm not expecting you to kind of get the details from these plots, but the take-home point is that you can see the pattern of the colors in this plot varies between the different metrics. So for example, if we look at the standard deviation here, you can see these blue points, which are these large boulder bed rivers from Taiwan. They've got very high standard deviations. They've also got quite high rugosity. But if we look at some of the other metrics, things like the frontal area and the effective slope, then they no longer are an outlier from that data set. So you can see that actually there isn't necessarily a consistent pattern between these different metrics in terms of the way that they're varying between the different rivers. So it's kind of suggesting that actually, you know, there is no single metric here that's going to describe all the properties of all these rivers. We might want to look at the relationships between them. So what we then did was we said, okay, well, what are the correlations between these metrics? And some of these metrics turn out to be quite highly correlated with each other because they're describing very different, similar aspects. So for example, there's a correlation between the range and the standard deviation. So what we did is we looked at this correlation data set and identified what's the smallest number of metrics that we need in order to describe all these different aspects of the surface. So we kind of removed all the metrics where we had similar correlation to try and produce a reduced data set. What we then did was said, okay, well, can we try and cluster these metrics? You know, which metrics are telling us similar things about the surfaces and which ones are kind of telling us different things. And therefore, what's the minimum number of different types of metrics that we need to describe these surfaces? So in this diagram here, we can kind of look at it in two directions. So this axis here is all our different metrics. So we've got three groups of the different metrics. And then this axis here is all our different rivers. And we've got 5 groups identified for the different rivers. And then all these warm and cold colours here are basically the value of that particular metric for that particular river relative to the other metrics for the other rivers. So if it's a red, it's a very large value for that metric. If it's blue, it's a very small value for that metric. So we can look at the kind of groups that have been identified by this hierarchical clustering. And so for the metrics, it identifies 3 different groups. The first one is all these metrics here. And these are basically all horizontal or vertical kind of roughness scales. So things like the standard deviation of elevation is one of the metrics that falls out in that group. So these are all kind of looking at the overall roughness of the surface, generally at a fairly large scale. This group of metrics here, these are all the kind of directional ones and the more sort of area-based ones. So the ones that look at either the total area of the surface or the slope. So things like frontal area and the inclination index are included within that group. So it's telling us that actually those directional metrics are telling us something different to just those overall roughness metrics. And then we've got a final group here, which is kurtosis and skewness. So again, it's saying that that might be explaining a different aspect of the surface. So actually those range of metrics identified in the engineering literature correlate quite nicely with the metrics that we've identified that we need to fully describe these surfaces. We've also kind of can group the surfaces, the rivers based on these metrics, and we get one group here, which is mainly those kind of quite exposed boulder channels. The second group, which is kind of fully alluvial channels, but with generally smaller boulders. The third one, which is bedrock dominated, but with some sediment cover. And then the final one are these Taiwanese channels, where we've got these very large sparse boulders. And if we look at the kind of the clusters of these different metrics, you can see that, for example, these channels here are identified by particularly large values of these directional metrics. These channels here are identified by particularly large values of these overall, these kind of average metrics. So what we kind of summarize from this part of the work is that actually, if we want to describe the rough bed river topography, we can't just use the standard deviation of elevations. We actually need to use multiple metrics to distinguish between those different topographies. And as a minimum, things like combining standard deviation, skew, and frontal area may well be sort of quite a good set. And that kind of findings, they're probably likely applicable to other geomorphic surfaces as well. However, like I said, our original plan is that we're trying to identify flow resistance. So this has kind of helped us to think about the range of metrics we need to consider, but we haven't yet actually considered any flow over these surfaces. So that kind of brings me on to the next part of the project. So the next part of the project that I want to talk about is some flume experiments that we did. So this was all using the flume at the University of Loughborough. So for any of you that haven't seen a flume before, it's basically a large indoor river. So we've got a pump which pumps water through this narrow channel. This channel is 60 centimetres wide. And then there's also a slope on the flume indicated by these red lines. So obviously water flows because of the pump and because of the slope. And we just keep flowing it over that surface and it recirculates around. So these experiments are also very much powered by Yorkshire tea. So what we did was a whole range of experiments where we kind of recreated some of our natural flume topography in the flume. And you might be able to see behind me, actually, some of these flume beds. There's flume beds that we created to give you an idea of scale. So we've got a smooth bedrock bed, an intermediate one, and a rough bedrock bed. We also added different amounts of sediment cover to this. So from up to 55% cover with scaled boulders. And then we also ran the flume experiments both with smooth walls and with also additional rough walls. One of the questions of doing flume experiments is kind of how representative are flume experiments of the kind of natural rivers that we're particularly interested in. So this diagram is to kind of convince you that, we have actually captured a lot of the variability that we saw in our original data set. So this is frontal area, this is skewness, and these small grey dots are those data sets, those elevation data that I showed you from our different field sites. The coloured dots are the range of different flume beds that we measured with increasing amounts of sediment cover. And what you can see is that the location of the flume beds, they plot pretty nicely on top of the scatter of the actual field sites. So it's kind of fairly reassuring that we do seem to be replicating a range of conditions, which is representative of the channels that we're interested in. So in terms of data collection, what we did for each of the experiments was collected a range of data. So essentially, ultimately, our aim was to measure the bulk flow conditions and then calculate the flow resistance value for that particular set of conditions. So this is the flume setup. So we've got a series of cameras on the flume, and these cameras were used to collect a lot of images of the riverbed so that we could basically reconstruct the surface topography of that surface. So we did that using structure from motion photogrammetry, and that data was collected when there wasn't any water in the flume. So we've got a very high resolution topographic representation of our flume bed. During each of the flume experiments, we basically ran a constant discharge, and we adjusted the elevation of a tailgate at the downstream end of the flow to try and get the flow so it was as uniform as possible. We've then got a series of water depth sensors and also velocity probes. So we measured the average elevation of the water at multiple locations along a 2-meter section of the flume. So if we know the discharge, because we set that in the pump, if we know the water depth and we know the slope, we can therefore back calculate the flow resistance for that particular set of conditions. We've also got velocity probes. So for some runs, we measured velocity profiles at certain locations within the flume. For each of the different configurations that we tested, so for each of the combination of bed and percentage boulder cover, we ran 5 different discharges, and we collected data from each of those different discharges. So these are the flume results from the smooth wall data. So in this figure here, so this is basically the relative submergence. So this is the hydraulic radius divided by the standard deviation of the bed. So these are deeper flows over here, and these are shallower flows over here. And on this axis here, we've plotted basically the inverse of flow resistance, which is maybe less intuitive, but it's more consistent with kind of what's been done in previous publications. So essentially, we've got lower flow resistance up here and higher flow resistance down here. So the coloured dots on this diagram are our flume data set, and then the grey dots are actually a compilation of data which was collected by Chen et al. So yeah, the Chen et al. 2020 data set. And I think first off, actually, what was just kind of reassuring is that our data do pretty much plot on top of their data. So it suggests that, again, we have actually managed to produce a set of flume experiments which are reproducing the processes that we're interested in, and again, do seem to be replicating or representative of the hydraulics that we see in natural channels. These data sets up here are kind of a bit of an outlier, and actually probably ones that we're going to remove from further analysis because we don't think that the flow conditions were quite right in those. Ideally, to be honest, we would have run experiments that were kind of further to the left on this diagram, and in some ways that's where there's a lot of scatter to the field data, but unfortunately we were a bit limited by the smallest flows that we can run just by the pump speed. So, this is kind of where we've ended up. So one of the things that we're interested in looking at is the way that the flow resistance changes with both the discharge and also with the amount of boulders which are deposited on that, which are stuck on that riverbed. So the first thing to say is that we've got this decrease in flow resistance as the discharge increases. And that's very much what we'd expect to see, and it's kind of commensurate with field data. So again, it's kind of reassuring. These figures basically show this relationship between flow resistance and boulder density for those 3 different beds. For the smooth and the intermediate bed, you can see we get this increase in flow resistance up to about 40% boulder coverage, and then we actually get a decrease as we move to that 50%, 55% coverage. This pattern of an increase and then a decrease, again, is actually consistent with some other experimental results, but the kind of percentage cover that we're getting at is actually quite a lot higher where we're getting that peak than what other people have previously identified. They had that peak at kind of lower percentage covers. So we need to kind of figure out, why we've got that sort of shift in our data. For the rough bed rivers, however, we didn't kind of get that increase and decreasing pattern. We kind of got a fairly constant flow resistance regardless of the boulder density. So the question is, okay, well, what property of the channel beds might explain those changes in flow resistance? And we can kind of come back to those different metrics that we looked at earlier. So these diagrams again show changes with boulder density, and this is the standard deviation, this is the skew, and this is the frontal area. And this is shown for both the smooth bed in black and the rough bed in blue. And you can see that for both beds, the standard deviation increases with boulder density. The frontal area also increases with boulder density. The skew for the rough bed is about constant. And then for the smooth bed, it kind of increases and then it decreases again. So it's actually showing us that none of those metrics seem to directly correlate with this pattern that we see here in terms of that flow resistance. So that sort of suggests there's no one single metric which is kind of going to solve the flow resistance problem. And again, for the rough bed, we've kind of got this constant here, and the skew is also constant. But again, the frontal area and the standard deviation seem to be increasing, which again is not consistent with that constant flow resistance. And the reason that we probably can't use any single metric to explain the pattern of flow resistance is because of the role of basically hydraulics. So if we think about the sorts of flow structures that are developing on these beds around these boulders, we're likely to get a sort of transition as we increase the density of those boulders. So when we've got just a single boulder on the bed like this, you kind of get this fully sort of recirculation zone that forms behind that boulder. And as the flow goes over that boulder, it's extracting energy from the flow, and that boulder is kind of producing form drag on the flow. As you start to get boulders which are closer together, we start to get wake interference. So rather than kind of this sort of full recirculation zone forming, each one is kind of interfered with by the kind of further downstream boulder. So we've kind of got this increase in flow resistance as we increase the boulder density because we're getting more energy loss from each of those different boulders. However, when the boulder density gets too high, you don't get that sort of full recirculation zone forming, and instead the flow just kind of skims across the top of all the boulders. So we've got this kind of transition from this kind of wake interference regime and through to this skimming flow regime. And we think that's probably what's happening here, is that we've got this sort of transition and we've got this skimming flow developing, and effectively the bed is kind of feeling smoother, despite the fact that the roughness metrics indicate that the bed has actually got rougher. In the rough bed here, we're likely to be getting different patterns just because we're starting with a rough topography, and actually adding boulders into that may actually kind of almost smooth out the topography rather than making it rougher in the same way that it does for the smooth bed. It's also kind of indicating that we have covered the range of conditions which are found kind of, or the range of hydraulics we'd expect to see in natural river channels. We can also, if our aim is to try and sort of improve this relationship, we can try and say, okay, well, does including extra metrics try and improve our predictions? So the black line here fitted to the data is the variable power equation, which was developed by Rob Ferguson. And it's basically a function of standard deviation. So what we're interested in is, does adding extra metrics to this equation, would that help improve our predictions? So what we've done is looked at the deviations between the points and this best fit line, and basically plotted that against the different other metrics. So this is plotted against skew, and this is plotted against frontal area. And for frontal area, there's kind of not a whole lot of relationship, but for skew, there is potentially a bit of a trend in the data, this kind of U-shape for the data. And actually this U-shape to the data is quite similar to, again, that reported from some of the engineering literature. So it might be that actually including skew would be a useful way of kind of trying to improve some of these predictions. So that's kind of as far as we've got to kind of with the smooth bed experiments, which Bobby very much led on. And then David Whitfield has been working in the last few months on running another set of experiments, but this time including rough walls. So he's been doing experiments with 7 different configurations here. So we've kind of been varying both the protrusion of the elements on the walls and also the spacing between them. So this is a kind of cross section of each of those walls, and you can see what the walls look like in this example here. So they're basically vertical battens, so the roughness is the same regardless of the flow depth. So we had 7 different wall configurations. We've got 2 different beds, so we use the smooth bed with both 10% boulders and 40% boulders. Again, 5 different discharges for each combination of walls and bed. And then we collected the same set of hydraulic data as in previous experiments. So again, if we plot our data on top of that sort of field compilation, you can see again, they do plot sort of quite nicely, you know, within the range of the other data. So again, it's kind of reassurance that the sort of hydraulics that we're replicating here, they do seem to be consistent with what we would expect to see in these sorts of channels. So we can then, we're interested in looking at is kind of how the flow resistance varies as a function of these different combination of bed roughness and wall roughness. So in this diagram here, this is looking at the flow depth, and then this is flow resistance on this axis here. So we've got low flow resistance and then high flow resistance up here. And then each of these lines indicates an individual combination of bed and wall roughness. And basically the colours tell you about the relative roughness of the bed and of the walls. So where you've got these yellow colours, that's where we've got very rough walls compared to the bed. Where we've got these darker blues, that's where we've got very smooth walls compared to the bed. So you can see that first off, when we've got rougher walls, we've got higher flow resistance, which again sort of makes sense. But we can also look at the shape of these relationships and the way the flow resistance varies with depth. And what we find is that actually when you've got kind of quite smooth walls, you might have a quicker decrease in flow resistance with increasing depth compared to where we've got rougher walls up here. And in particular, in some of these relationships, particularly for the rough bed, we've actually kind of got this U shape to the data where we actually get a decrease in resistance. And then actually as it gets deeper, it actually starts to increase again as we're kind of getting an increasing influence of the rough walls compared to the sort of relatively sort of smoother bed. And this kind of U shape to the data is actually consistent with what we've seen in some of our field data sets. So this is some data that actually Bishnu Sharma collected for part of his PhD that Rob Ferguson wrote up. And you can see in this example here for Trout Beck and this reach, as we increase the discharge, we get a decrease in roughness, and then we actually get this increase in roughness again for higher discharges. However, in other parts of the same system where we had a rougher bed, we actually didn't see that relationship. So this kind of, this U shape to the data is consistent with some field examples, although interestingly, it's kind of the opposite here, that in the field we saw it in the smoother bed, and in the flume we're seeing it in the rougher bed. So we need to do a bit more sort of thinking about why we're kind of what the processes are that are going on and why we're seeing that. We've also tried to kind of start to understand again what that pattern is between the friction factor and the particular properties of that roughness on the walls, and thinking about ways that we can try and sort of measure that wall roughness. And a parameter that's been identified in the literature is this parameter of cavity spacing divided by protrusion. So it's basically saying how big are the gaps between those battens compared to the extent to which those battens are sticking out. So over here, we've got very small spacing between the battens. And over here, we've got very large spacing between the battens. And you can see again, we've got maximum flow resistance at this sort of intermediate cavity spacing and protrusion ratio. And this is very likely to be another sort of transition between the flow regimes. So again, over here, we've got very small spaces between the battens. And so this may be where we've got more like a sort of skimming flow regime. So we're not actually, there's not enough space between those battens for that sort of full recirculation eddy to develop. Over here, the walls are essentially smooth and we've got very small sort of isolated battens sticking out. So they're not having a lot of impact on the flow. And it's in this kind of intermediate regime here where we've kind of got this wake interference regime where we've kind of got that maximum impact of the battens on the flow near to the walls. And just to kind of give you an example of a bit what this looks like, this is a sort of video looking down onto the flume, and you can, it's a bit of an eye of faith, I'll give you that, but you can sort of start to see that there might be some sort of flow structures which are developing around these battens, and you can see that sort of almost wake flapping type structures kind of coming off the leading edge of those battens. So to kind of summarize kind of where we've got to with these flume experiments, I think, like I said, this is very much work in progress that we're kind of trying to analyze and write up at the moment. But I think where we've got to is, you know, we're pretty convinced that the flume experiments we've conducted, they do seem to be a good representation of natural channels. So therefore, you know, we're hopeful that the findings that we get out of them will say something more broadly applicable and hopefully more useful for making predictions in upland channels. I guess that variable power equation, to be honest, to a first order, it actually doesn't give a bad prediction from our flow results. You know, so it might be that looking at that relative submergence relative to the standard deviation of elevations is actually not a bad starting point. But there is still scatter in that data, and we'd like to try and think about how we can try and improve that scatter, particularly because if we look at other sort of relative submergences, there's a lot more scatter in that natural data set that we'd like to try and reduce. So our kind of working sort of hypothesis of kind of what we're going to take forward is that actually looking at skew might be an important thing to try and add into these relationships in order to kind of improve the predictions. But we also kind of need to do some work to try and better understand the hydraulics in this system and actually understand the way in which that topography is affecting the flow. And that might also help us sort of identify what it is that we need to include in the new predictive equations. So to kind of do that improved understanding of the hydraulics, this is the part of the work that Thais is working on. And so what she's been developing is some CFD modeling. So she's been developing some two-phase CFD. So because we've got a very rough bed, you get quite an irregular water surface. So therefore kind of standard one-phase rigid lid models where you just kind of assume a flat water surface weren't working very well. So she's had to develop some two-phase models where you model the water and the air as well. So essentially what she's currently doing is replicating those flume experiments in a CFD in a computational fluid dynamics model. She's been using those velocity profiles that we measured in the flume to validate the model. And this is an example of that. So again, this is velocity here, elevation here, the points are the measurements from the flume, and the solid line is from the model. And you can see there's a pretty good agreement between the two. So we're fairly confident that the CFD models are actually replicating our flume experiments quite well. And then the next thing that Thais is going to be doing is really looking at the kind of pattern of CF results across these CFD models. So this is an example of the output of one of those models. So this is the bed topography. And what we're looking at is particularly the pattern of dynamic pressure across the bed. And the reason for looking at dynamic pressure is because as the flow moves from a high pressure zone to a low pressure zone, it basically loses energy. So those obstacles on the bed, they cause spatial variations in the dynamic pressure on the bed, and they basically cause form drag, which loses energy from the flow. So by looking at the pattern of those pressures, we're hoping to basically kind of sum up the total amount of form drag, but also we're interested in looking at the types of topography that produce those drop-in pressures. So we're interested in looking at the particular scales of topography. which cause the drop in pressure, and also the way that those patterns change as a result of increasing discharge. So for example, if you look in here, this is our low flow condition through to a higher flow condition, and you can see that not only does the size of the pressure differences increase as we move from low flow to high flow, but also the spatial extent of some of those patterns increases. So you can see there's some areas that kind of transition from being sort of negative pressure here to actually being positive pressure. So again, this is quite early days and that we've only recently sort of got the CFD results, but trying to start to unpick those relationships between that topography and that pressure. And hopefully that again will help us to identify what sort of metrics we should be using to describe the topography, and therefore kind of that will feed back into those sort of analysing those flume experimental results, and hopefully maybe producing some new sort of predictive equations. So to kind of conclude with where we are at the moment, I think, you know, a lot of this work has really been sort of started from this idea of actually this high resolution topographic data, which is now widely available. And, you know, and that's really enabled us to do that analysis of all the different metrics, but also to run those flume experiments where we've actually been able to replicate those natural riverbeds in the flume. So I think there's a lot of sort of exciting avenues that we can kind of build on from having that topographic data available. And then I think kind of the one, I guess, big caveat to this is that at the moment, a lot of the techniques that we've got, they only really work on exposed surfaces. We don't have as good techniques for looking at riverbed topography when that riverbed is underwater. So actually, I guess sort of going forward after this project, one of the things to think about is how we can take the findings from this project, but actually apply it to situations whereby we maybe don't have such good sort of topographic data from the riverbed. And we're also going to be thinking about how we can make sort of maybe more like rules of thumb or kind of simplified relationships that will hopefully improve predictive ability, but won't sort of be required quite so the sort of same topographic data sets that we're working on at the moment. And with that, I will leave that there.
I will draw it to an end and say thank you very much for that wonderful presentation and a last round of applause. Thank you again.